We're going to talk here in section 4.3 about making the connections between the graphs of f prime and f double prime with the graph of the function f. So we have kind of a list here of the things that we need to be able to recognize. So if we know one thing about the graph of the derivative is that if the original function f is a polynomial, then it has to go down in degree. So when we look at the blue function at the right, that looks like a cubic. So we would expect that its derivative would need to be a parabola of some kind. Second thing is we want to look for horizontal tangents. So any place that there's going to be a relative minimum or relative maximum in the original function is going to correspond to an x-intercept in the graph of the derivative. I'm going to come back to these to number 3 in a minute, those kind of places where the derivative doesn't exist, but we need to recognize and know how the graph of f prime will look when we encounter those kinds of strange things happening. We also need to recognize that when the original function is increasing, then our derivative must be positive, and when the function is decreasing, the derivative must be negative. And then we'll combine that with any place the original function has a point of inflection, an inflection point, then that's going to correspond to a relative min or max in the graph of the derivative. So seeing what we're looking at here, the original function here is increasing. It looks like there's, so it's going to be positive, so it's going to come down something like that. Then it's going to start to decrease along here, so it's going to go into a negative. And then somewhere in around this area here, there's going to be an inflection point. And that's going to correspond to the place where the derivative is the negative tangent lines is going to reach its steepest tangent line there, which will be the largest negative value of the derivative. So that's going to come into there. Now it's going to continue to be negative, but it's going to the tangent lines will flatten out. So the slopes of those tangent lines will get smaller and smaller until they hit 0. Then they're going to become positive and going smaller positive to bigger and bigger positives. And we're going to get something that's going to look like a big parabola. So let's take a look in the bottom row here about what the derivative will look like at these kind of unusual places. So there's lots of different kinds of discontinuities we can have, but in this case, with the vertical asymptote at the x-axis, we can see the slopes of the tangent lines are close to 0, but a little bit positive, and then get bigger and bigger and bigger positives. So we're going to get something, and it's going to look something like that. That kind of chimney, that space between the y-axis and the curve is going to get a little bit bigger. You can see that algebraically because if f is 1 over x, then its derivative is going to be negative 1 over x squared. And so as you put in a small number there, it's going to get bigger faster. So for example, if you plug in a half, for the value of the function at 1 over x at a half, the value would be 2. But when you plug it into the derivative, you would get 1 over 2 squared is 1/4, which would give you 4. So there's going to get a little bit steeper, a little bit faster, which gives it more space between the curve and the y-axis. Likewise here, we're going to have very big negatives, and then it's going to flatten out towards 0, big positives rather, but it's going to flatten out towards 0, so we're going to get something like the volcano graph. For the absolute value or the corner point here, the slopes along here are going to be the same negative value at this particular point. The corner point, the derivative is going to be undefined, so you'll get a horizontal line, and at whatever the slope of that negative part of the decreasing part of that absolute value, and then it's going to become a positive value, and it'll always be the same there. The third one is going to be a cusp, which is going to result in a vertical asymptote. No, I didn't do that very well. Trying not to make the screen jump my reaching over with my left hand. So this looks like it's going to be close to 0. Then it's going to get positive, bigger and bigger positive, and it's going to go to positive infinity. On the other side, it's going to be a very steep negative, and then it's going to gradually approach 0 coming from below. So in a cusp, you're going to get a vertical asymptote in the derivative, but it'll go to different infinities. So this is a cusp right here. And here we have the vertical tangent, and we can see that originally somewhere over here it looks like it's about 0, and then it's going to get bigger and bigger positives, and it's going to go to positive infinity on the left. When we hop over the asymptote, that's still very steep positives, so it's going to also go to the same infinity. So vertical tangents, you get a vertical asymptote, and it goes to the same infinity. I'm going to get a new screen here. Let's talk a little bit about concavity here. So the graph of a differentiable function y equals f of x is concave up on an open interval I if f prime of x is increasing. So always with concavity we're going to have open intervals. And you can see on the yellow curve here, the slope of the tangent line here would be negative, and then it goes to 0, and then it goes to positive. So as you move your way across here from left to right, the slopes of the tangent lines are increasing. That means f prime of x is increasing. And that's also why down here you can see our test for concavity is that the derivative of the derivative would be positive. So f double prime of x is positive is how we're going to test for concavity. Another way sometimes it is described is a function is concave up if it lies above all of its tangent lines on that interval. That comes up from time to time. Also, we see that a function is concave down if f prime is decreasing. So here we have on this green concave down curve that the slope of the tangent line here is positive, then 0, then negative. So those slopes of the tangent lines are decreasing. That is, f prime of x is decreasing, which means its derivative is going to be negative. So, and again, an interval is concave down when it lies below all of its tangent lines on that interval. Okay, let's look at the example down here. So where is this function going to be concave up? Where is it going to be concave down? So that question, when we're asking concavity, is a second derivative question. So we'll first find f prime of x and say that's going to be 3 plus cosine x. Then we'll find the second derivative, and that's going to be just a negative sine x. We want to know where that's equal to 0. So where the second derivative is 0 or undefined is known as the pips, that is the potential inflection points. And so doing the same kind of thing we do with the first derivative, only with the second derivative, sine is equal to 0 at multiples of pi. So that's going to be at 0, pi, and 2 pi. We'll do our number line sine analysis, and we're just looking at this interval from 0 to 2 pi. And we know pi is going to be halfway in between. If we plug in a number in between 0 and pi, say pi over 2, sine of pi over 2 is 1. The negative of that would make it a negative 1, so it's going to be negative in that interval. And to the right of pi, say at 3 pi over 2, sine of 3 pi over 2 would be a negative 1 times a negative makes that positive. So we would say then that the function f is concave down on that interval from, we could either use interval notation and say 0 to pi, or we could say 0 strictly less than x, strictly less than pi, and we could say f is concave down on that interval from pi to 2 pi, or likewise we could say x is between pi and 2 pi. Notice they are open intervals. So point of inflection is a point where the graph of the function has a tangent line and where the concavity changes. That's known as a point of inflection. So kind of a little trivia there. The derivative could be undefined at a vertical tangent, but that still has a tangent line there. So that would still be considered a point of inflection. If you had a place where there's a corner or a cusp or something like that, and it changed concavity, there is no tangent line there. That wouldn't actually be considered an inflection point, but that's pretty much splitting hairs there. So let's look at this. We have a graph. The yellow here is f prime of x, and so looking at the derivative, can we determine on what intervals is f increasing? So f will be increasing when the derivative is positive, but the fact that it's 0 here at -2 is still positive on either side, so it's going to increase through that entire interval. So it's not clear whether this thing goes on and on forever. Let's just say, to make our life a little easier, I'm going to put an endpoint there and an endpoint there. So we can know that this is only defined on that interval from -3 to +4. So then where this is increasing is going to be where the derivative is positive, and so that will be from, we will say, from -3 to +1, and we'll include the endpoints there. Now, the interval where it's concave up is going to be where the derivative is increasing, and so that's going to be along this part of the curve here and also along this part of the curve here. And remember that we don't include endpoints on intervals where the function is concave up, so we will say on that interval from -2 to 0, and also on the interval from, I guess that's going to be roughly, I didn't do that very good, say 2.5 to 4, I'm guessing there. There's a little room for interpretation on that left endpoint. Part C, what are the x-coordinates of any relative extrema? We're going to get relative extrema where the derivative changes sign. So certainly at x equals 1, we can see that the derivative changes from positive to negative, which is going to make that be a relative maximum. Now remember, we can also get relative extrema according to our book. Now this would never be an AP question because different textbooks interpret this differently, but we can see that on that endpoint, if we're graphing f, that whatever value that is at -3, because to the right of that the derivative is positive, the function must be increasing, which would make that point at -3, according to our book anyway, be a relative minimum at x equals -3. And likewise at that other endpoint over here at 4, to the left of it the function is decreasing, so it's falling from left to right. That's going to make that also be a relative minimum at x equals, I think I called that 4. Coordinates where we have points of inflection are going to be where we change concavity, and that's going to be at, I'm going to change colors here a little bit, that's going to be any place where we see a relative min or a relative max in the derivative, because here the function is decreasing on one side, which means it's going to be concave down, then it's increasing on the other side, which means that if the derivative is increasing, that means that the original function is concave up. So we will get inflection points at x equals -2, also at, I'm going to just say that's 0, and I think we called that 2.5 earlier. A very good positioning of my curve there. Can we sketch a graph of this? Let's see if we can do that. And let's say, now we have no y values, so I'm just going to start the curve, say right here. It's going to be increasing and it's going to be concave down until we hit this x value right here. That now is going to be an inflection point, but then it's going to go back to increasing again. So that is going to make that be, then a shelf point is going to occur right at x equals -2. So it's increasing to the left and to the right, but it's changing concavity. Now at the 0, it's still going to be increasing on either side, but here it's going to change concavity. So we're going to go until we get our relative maximum at x equals 1. Now it's going to start to decrease, and it will keep decreasing. Once we get to that x equals 2.5, we're still going to be decreasing, but now it's changing concavity until we get to that endpoint there. So something that looks like that would be a possible sketch. Again, the y values we don't know, so anything that is moved up or down would be acceptable. It should have just that same general shape.